All right, so today is going to be our final lecture on network flow. And I want to start off by remembering two of the lemmas that we used last time to prove that the Ford-Fulkerson algorithm is correct. I showed that if you had these lemmas, you could use them to prove correctness of Ford-Fulkerson. But now I want to prove the lemmas because I didn't prove the lemmas last time. And then after that, I'm going to prove the max flow min-cut theorem, which I stated last time but didn't prove. And then after that, I'm going to show you some relationships between max flow and LPs and duality, and how duality is here is related to the min-ST cut problem. And then I want to show you one application of flow to a problem. Okay. So good. So let's prove lemma 1 first. Right, where in lemma 1, I'm using m to denote the number of edges in the graph. So we'll prove it. We can prove it by induction on m. Okay. So the base case is m equals 1. There's only one edge in the graph. So here's S and here's T. So there's only one edge. This is the edge. Right? And whatever flow you put on that edge obviously decomposes into one path. Right? It is a path. It's a path of length 1. The inductive step suppose it's true that for smaller graphs, for graphs of size at most m-1 edges, the statement is true. Then why is it true when you have m edges? Well, let's look at the flow itself as a graph. Okay, so each edge that has positive, let's show that kind of true for m-1 implies true for m. So this flow is routing. This flow is a vector. Right? It's a vector indexed by edges in the graph, and to each edge it's assigning a number, and these numbers have to obey certain things like conservation of flow, non-negativity, the constraints of flow. But anyway, it's an assignment of numbers, of non-negative numbers to edges in the graph. So let's define a graph, which is the same vertex set. And what are the edges? The edges are any edge in the flow that has strictly positive, that is non-zero flow. So define a graph G prime, which has the same vertex set and a set of edges E prime, where E prime is the set of all edges such that FE is strictly positive. It's not 0. Okay? And two cases. Case 1 is the value of this flow is not 0. It's positive, okay, which means there's something leaving S. So just try to do a DFS starting at S in this graph G prime. So we know that since there is some positive flow being pushed, there is something that's leaving S. And just follow that and keep going, okay, until either you get stuck, right? There's no out edge, or you have a cycle. So DFS from S until case A, you get a cycle, and case B is you get stuck. Now, if you have a cycle, great. That means we've just found a cycle in this graph. Take the minimum flow on any edge in that cycle, okay, and subtract that from every edge in the cycle, and then remove that cycle from the graph and iterate. What have we done? We've now reduced the problem to the case where m is strictly smaller, right? Since we took the minimum flow on any edge in that cycle and subtracted it off, one of the edges in that cycle, namely the one that had the min flow on it, now has 0 flow on it. So we've decreased m by at least 1. So now we have a new graph, a new flow graph with strictly fewer edges, so we can apply the inductive hypothesis. So we took off a cycle, then what we have left can be decomposed into paths and cycles, so overall we have paths and cycles. The other case is that we get stuck. Okay? There's no out edge. Now, can we get stuck at a vertex which is not t? And the answer is no. Now, first of all, if we got to S, that's a cycle. So we either got stuck at t or something that's not t. Can we get stuck at something that's not t? And the answer to that is no, because of conservation of flow, right? Wherever we got stuck there because we entered it. So if we can enter it with a certain amount, there's some flow on that edge that's entering it. We know that that amount of flow has to exit it as well. Okay? So by conservation of flow, we can't possibly get stuck at a vertex which is not t. That means we got stuck at t, which means we just found an ST path. Okay? We started at S, we ended at t. So again, take the minimum flow along any edge on that path, decrease the flow on every edge in that path by that amount. One of those edges now gets down to zero flow. So we've decreased the number of edges in the graph, in the flow graph by 1, iterate. And by our inductive hypothesis, this new smaller graph can be decomposed into paths and cycles, plus the one ST path we just found. Okay? That's that. It might be the case that, case 2, that the value of f is 0. If the value of f is 0, that means there's nothing leaving S. Okay? So in case 2, and as we're going to see from a lemma later, it turns out, I haven't proven it yet, that the flow out of S equals to the flow into T. Okay? So if we know in case 2 there's nothing leaving S, we also know there's nothing entering T. So if we're in case 2, there's nothing leaving S, there's nothing entering T, the value of the flow is 0, okay? And f, let's say, I'm assuming here that f is not the 0 vector. So first of all, I'll just say it's trivial if f is the 0 vector, right? Then it decomposes into 0 paths and cycles. So we're assuming here f is not the 0 vector. So here's S, here's T. There's nothing coming into S, there's nothing leaving S, there's nothing coming into T. So there's no out edges in this flow graph, there are no in edges here, but there is something that has positive flow somewhere. This edge has positive flow. So that's in the flow graph. But what do I know? Again, I have conservation of flow, right? Which means that if there's flow coming into B, there must be flow going out of B. And then whatever this is, if there's flow going into that, there must be flow going out. So I can just keep following this path, and eventually, I cannot get stuck. Eventually, I have to hit a cycle, right? Because of conservation of flow. Eventually, we'll cycle. I can't get stuck, cannot get stuck, due to conservation of flow. So again, now I found a cycle. I can decrease all the edges on all the flows on those edges by the minimum flow on any edge in the cycle, and then repeat, use my inductive hypothesis, and then decompose what's left. So that's it. That's the proof of lemma 1. I don't want to do the proof of lemma 2 on the board because it really is just a consequence of the definition, okay, of the residual graph. What do you need to check? What does it mean to be a valid flow? You need to check that this obeys conservation of flow. And by the way, if some of the entries here are negative, that means you flow in the reverse direction. Okay? So you just need to make sure that this obeys conservation of flow, okay? And that it obeys the capacity constraints in GF. Those are two computations that there's nothing clever about them, so I'll leave that to you. Okay? So lemma 1 and lemma 2 we saw last time combined imply the correctness of the Ford-Fulkerson algorithm. So now I want to prove this other main theorem from last time. Another theorem from last time. We had this theorem that max flow equals min, so I should say specifically max ST flow is equal to the capacity of the min ST cut. Right? So what I'm saying is the value of the max flow is equal to the capacity of the min cut. Okay? So before I prove this theorem, let me prove a lemma. And recall, actually before I write down the lemma and the proof, just recall an ST cut, capital S, capital T, is a partition of the vertices such that little s is in capital S and little t is in capital T. Okay? And we defined the capacity of that cut as the total capacity going from the S side to the T side. So this is equal to the sum over all edges AB in the edge set of A being in capital S and B being in capital T of the capacity of that edge. Okay? So imagine here you have S, here you have T. There's some cut here, so there's capital S here, capital T here, and there are some edges that are crossing that cut in either direction, from T to S or from S to T. We're only looking at the ones that cross in this direction. So U of S here means the total capacity of the pink edges. All the edges that cross the cut in the S to T direction. Okay? And I want to give one more definition before I state the next lemma. Let's define the net flow across a cut let's call that f of capital S. So f is a flow here. It's a vector indexed by edges. And when I write that vector parentheses capital S, that's the net flow. And what that means is it's the sum of all u in capital S and t in and v in capital T. So little u is in capital S, v is in capital T, of the flow uv minus the flow vu. Okay? So what's that picture? So the net flow, if I had to draw a picture, here again I have S, here I have T, there's some cut here. This is the capital S side, this is the capital T side. Okay? And there are edges crossing possibly in both directions. So there's some edges that go from S to T. And there are also some edges that go from T to S. And net flow is equal to the pink flow minus the blue flow. So flow that comes in the reverse direction gets subtracted. Flow that goes in the forward direction toward capital T gets added. That's net flow. Okay? That's the definition, my definition of net flow. So now my lemma, okay, is that for all flow vectors f and for all st cuts st, if you look at the net flow of S, that's just equal to the value of the flow. Okay? So when I defined the value of the flow, I said that it's the flow leaving S. But if this lemma is true, it also implies that it's the flow entering T. Okay? Why is that? Well, what is, let's look at, so note, by definition, val f is just f of the set only containing little s by itself. Flow doesn't come into the source, right? It only goes out of the source. And similarly with the sink, flow only goes into the sink. And the lemma implies that val f is also equal to f of the vertex set minus t. What is this? This is the flow entering T, little t. Right? It's the flow going from everything that's not little t into little t. So it's the flow that's entering little t. So this lemma implies, for example, that we could have defined the val of f in either way, and it would have given the same result. How do we prove this lemma? We'll also prove this by induction. By induction on the size of S. What's the base case? The base case is that capital S has size exactly 1. Well, why does it hold when capital S has size exactly 1? Remember, by the definition of st cut, little s has to be in capital S. So if capital S has size 1, this implies that capital S is just little s. And we know, as we said up there, that f of the set only containing little s is equal to the value of f by definition. Okay? So we're good. The base case holds. How about the inductive step? Okay. So let's suppose that it holds for all capital S's of size up to k, and now we're trying to show that it holds for some capital S of size k plus 1. So let's draw a picture. So let's say here is T, here is capital S, and this capital S has size k plus 1, and we're trying to show that it's true. We know little s is in here, and since capital S has size at least k plus 1, it has size at least 2, we know there's some other vertex in here which is not little s. Let's just pick an arbitrary one and call it V. Okay? Now, as a thought experiment, let's imagine moving V to the other side of the cut. Okay? So now over here, this is S minus little v, and this is T union little v. Okay? And let's ask ourselves, what is, so f of, let's look at f of S minus little v. It's some number, right? It depends on It depends on the total flow of edges that go across this cut minus going backwards. A lot of that stuff doesn't depend on little v at all. Let's look at which of that contribution to this net flow actually depends on little v. Well, there are 4 types of edges involving little v. There are some edges that from little v go into s minus little v. So there are edges that look like this. There are also edges that start on this side and go to little v. There are also edges that leave little v but stay on the t side. And there are also edges that start on the t side and go to little v. Right? Now these 4 types of edges contribute 4 sums to this overall net flow. Let's just give these now 4 sums names, okay, variable names. So let's say that the total amount of flow from v to the s side is capital A, and the total amount from v, let's say the total amount from v to the t side is capital B. The total amount from the s side into v is capital C. And the total amount of flow from the t side into v is capital D. Okay? So there are these 4 types of edges. All the ones that go from v to the s side, in total, their total flow is capital A, etc. Now, what do I know? Let me write this over here. So this side of the cut is T union capital V. What do I know? I know I have conservation of flow. Flow out of V equals flow into V, which means that A plus B is equal to C plus D. Right? Now, in terms of what is from these 4 types of edges, which ones contribute to f of s minus v? Not all of them do. Remember, the ones that contribute to this net flow are the ones that cross the cut in either direction. Right? So for example, B and D don't cross the cut. Right? Because all these vertices, V and all these ones that are pointing into V or out of from V, are on the T union V side of the cut. So in this cut, they don't actually cross the cut. Right? So B and D don't contribute to the net flow, but A and C do. And what do they contribute to the total net flow? They contribute, I guess, C minus A. Right? Because it's the things that flow from the S side to the T side minus the things from the T side to the S side. That's the definition of net flow. Right? So I said it's the pink flow from the S side to the T side minus the blue flow. So the contribution amongst this flow to that is C minus A versus what if we had just left V on its original side? Remember, V was supposed to be an S. What if we had left V there? Then what would change? A and C wouldn't matter anymore, right? Because A and C involve vertices that are on the S side, and now V is also on the S side. The flow that would contribute to the net flow, the flow that would contribute to f of capital S, would be the flow to this side, which is B, minus the flow toward V, which is D. So it would be B, so versus B minus D. Right? So what we just said is, in the smaller cut, the cut where you only have, where V is not on the S side, the total contribution to flow involving V, to net flow involving V, is C minus A, versus if you put V on that side, the total contribution to the net flow is B minus D. But lo and behold, these are equal because of this, because of conservation of flow. Right? A plus B equals C plus D. So just imagine rearranging, subtract A from both sides, subtract D from both sides. You get C minus A is equal to B minus D. These are equal to each other, which means that this net flow is equal to that net flow. But by the inductive hypothesis, remember this S is one size smaller. By the inductive hypothesis, this is equal to the value of F, which means that's equal to the value of F. Okay? So what this lemma is telling us is, no matter how, the net flow for any cut is just equal to the value of F. Okay? And the key in this is the fact that you have conservation of flow. That's what really makes this lemma true. Okay, so now we know that we have that lemma. Let's use it to prove the max flow min cut theorem. Okay. So why is this theorem true? So let's say that F star is the max flow, is a max flow, and capital S star is a min cut, min ST cut. I want to show that the value of F star is equal to the capacity of S star. One way to show that x is equal to y is to show that x is at most y and x is at least y. If those are both true, the only way for that to be true is that x equals y, right? So how can I show that let's say x is at most y. So for step one, I want to show that the value of F star is at most the value of S star. Okay. Well, that's easy enough. The value of F star is equal to the net flow across the cut S star. That's the lemma that we just proved. Okay. Which is equal to the sum of, let's say, U in S star and V in T star of F star UV. This is F star. F star UV minus F star VU. Remember, flows are non-negative vectors. So this number here, F star VU, is a non-negative number. So minus it is non-positive. So this is certainly at most that same sum over the same things of just F star UV without subtracting that. And because of capacity constraints, the flow on the edge UV can be at most the capacity of the edge UV. So that's the sum. So let's say here E is equal to UV, where U is an S star, V is in T star of F star E. That's at most that same sum over the same stuff of U of UE, which is just the definition of US star. Right, so we just showed that the value of star is at most US. Right. Cuts don't have values, they have capacities. This should be the capacity. Right, so that's exactly what we wanted to show, so we're happy. So now we need to show the other direction. Right, we need to show that the value of F star is at least the capacity of the min cut. So in fact, they're equal. So now we want to show that the value of F star is at least the capacity of S star. Okay. So I will show you, we'll show that there exists some flow F and some ST cut capital S such that the val of F is actually equal to the capacity of S. I'll show you that. Okay? And once we have that, we're done. Why? Because the capacity of S is certainly at least the capacity of the min cut. That's the definition of being the min cut, right? And similarly, the value of F is certainly at most the value of F star. Because F star is the max flow. It's the thing that has the most value. So we would have, so what I need to show you is, I will show there exists an F and S such that this is true. Right? And once you have that this highlighted thing is true, you get what you want, because this is at most value of star, and this is at least the capacity of S star. So the question is, why is there a flow and a cut such that val F equals US? And to prove that, I'm going to use for the Ford-Fulkerson algorithm. So we will obtain an F and S from the Ford-Fulkerson algorithm. So let me just define them, and then I'll draw a picture to remind ourselves of what Ford-Fulkerson was doing. OK, so I'll just define F to be the flow output by the Ford-Fulkerson algorithm. Okay. And I'll define capital S to be the set of all vertices V such that little s has a path to V in the residual graph GF. Right? So let's just do an example. So that's it. That's the definition of little f and capital S. Let's draw an example. Remember that graph we had last time? Okay, that was the graph from last time. Let me give these vertices names, A and B. And we saw that the max flow of this graph is this. So we flow 10 this way. We flow another 10 this way. And then we flow a final 10 this way. That's the flow that Ford-Fulkerson would return. So what does GF look like? Well, it has the same vertex set. We've only used 10 of the capacity in this down edge, which means we have 10 left, but then we also have 10 reverse capacity. So we have this situation, 10 this way and 10 this way. And then we've used all the capacity in these two edges. So the reverse edge has capacity now. So we have this edge with capacity 20, the reverse edge with capacity 20, and this reverse edge with capacity 10. Similarly over here, we have this, we've used all the capacity in this edge, because this is flowing 10 on it, this is flowing another 10 on it, which means we have this backwards edge with capacity 10, and similarly here we have this backwards edge with capacity 10. Okay. What can little s reach in this graph? Nothing, other than itself. Right? So in this example, This is the S side, and this is the T side. And lo and behold, what's the capacity of this ST cut? Well, let's look at the original graph. It's just S by itself. The total capacity going from S to the rest of the graph is this edge plus that edge, 20 plus 10 is 30. Okay, so in this example, it gave us 30, which actually is the value of that flow. Okay? So that's just an example. Why does this always work? So let's think about more generally. So let's look at the residual graph GF. There's some S here. There's little t here. There's the things that capital S, there's the things in the residual graph that little s can reach, and there's things it can't reach. Let's say that boundary is somewhere here. So this is capital S, this is capital T. There are some edges that are crossing this boundary. Okay. Now, what do I know? What's the net flow? I know that the net flow, f of capital S, is equal to the value of f. Okay. Now, all of these pink edges must be fully saturated, right? Why? By definition of capital S, all of these vertices on the S side, at the base of the edge, all of them are reachable by little s. That's the definition of capital S, right? It's all the things that are reachable. So all these things here are reachable, but these things are not reachable, right? Because they're on the T side of the cut. Which means there's no residual capacity left in any of these pink edges, right? So all these pink edges are fully contributing to our net flow. Okay? Now, are there any reverse edges that are coming backwards? Are there any edges that, in the residual graph, so let's look at edges that might look like this. Yeah, so if I look at any edge that's going from the T side to the S side, could that edge possibly be pushing any flow? If it were pushing any flow, that means there's some capacity in the reverse edge, right? If there were any edges in the reverse order like this that were pushing flow in F, I would have residual capacity in the reverse edge. And since this thing is reachable, that would be reachable in the residual graph. But that's impossible because I just said that, my example was this thing is on the T side of the cut. Right? Which means that any edge that could be possibly contributing to the net flow in the reverse direction isn't. Because if it were, the base of that edge would actually be on the S side. It would have been reachable. So none of these exist. Which means, strictly speaking, what I just showed is that therefore I have nothing that's subtracting from my net flow. All the pink edges are fully added into the net flow. So this thing is certainly at least the capacity of that cut, because I'm fully saturating all of these pink edges. Okay. And in fact, that's it, because I said the pink pink is the set of all edges that cross the cut from the S to T direction. So there is no other flow there's no other edge that's going across here. So that's it. These things are actually equal. Okay. So I'm done. I've shown you that there is an F and an S, namely we get them out of the Ford-Fulkerson algorithm such that the val of F is equal to the capacity of S, and we have the reverse direction of the inequality that we wanted. Okay. And in fact, since we know more generally what we actually, just the same proof as item 1, in fact, we know that for all F and for all S, we have that, in fact, the val F is at most the capacity of S. Right? It's the same exact proof of item 1. So, so I guess we're done, right? So we know that val F star is at least US star. We also know that val F star is at most US star from there. Therefore, whatever's in the middle here, since these two things are equal, it means whatever's in the middle is also equal. Actually, I didn't even need to say this. Right? Whatever's in the middle is also equal. Therefore, the val of F is actually equal to the val of F star, and this is actually equal to the capacity of S star, which means this is the max flow, and this is the min cut. So we talked about an algorithm for max flow, namely Ford-Fulkerson. Now we also have an algorithm for min cut, namely run Ford-Fulkerson, get a flow, and then do a DFS to define capital S, okay? And then lo and behold, now you have the min cut. So we have an algorithm for min cut with the same runtime as max flow. Okay? Good. So now what I want to do is I want to relate this back to linear programming and linear programming duality. To linear programming. And let me do this with an example. Let's say I had the following graph. And let me write down the edge capacities. So let's write down an LP for the max flow problem. So I want to maximize the flow, which I know the flow is equal to the value of the flow is equal to the total flow leaving the source S. So I want to maximize. First of all, what are my variables? My variables, I have one per edge, namely the amount of flow on that edge. So I have variables that look like f of SA, f of SB, f of AB, f of AT, and f of BT. Okay? So I have 1, 2, 3, 4, 5 variables, one per edge. So my vector C, remember I'm trying to maximize C transpose X. My vector C has dimension 5. So it's going to look like max of 1 times FSA plus 1 times FSB plus, and then the rest are zeros. right? 0 times FAB, 0 times FAT, and 0 times FBT. Because all I care about is the flow that leaves S. And the only edges that leave S are these two edges. So C is a 5-dimensional vector that has 2 1s and 3 zeros. Subject to constraints, I have the capacity constraints, which say, for example, f of SA is at most 3, f of SB is at most 2, etc. These are the capacity constraints. And then I also have the conservation of flow constraints, which need to be there for all the vertices which are not S or T, which means, in this example, A and B have flow conservation constraints. So it says that the flow into A has to equal the flow out of A. Okay? But remember now, in linear programming, the way we talked about it, whenever you have a constraint, the left-hand side is some linear function of the variables, and the right-hand side is some number, right? AX is at most B, where B is just a vector of numbers. So I'll write that as, so flow into A has to equal flow out of A. I'll write that as f of little sa minus f of AB minus f of AT is equal to 0. So this is my right-hand side, right? I just moved these two things over to the left. And then I also have something for B, which is that the flow into B, which is FSB plus FAB minus FBT, is also equal to 0. This is flow conservation. And then I also have that every entry of F, all these 5 variables have to be non-negative, non-negativity of flow. Okay? So that's the linear program that corresponds to this, this graph. Let's try and write its dual. Let's just remind ourselves what duals are supposed to look like. I'll do that on this board, and then I'll go back there. So if we have the primal LP looks like max of C transpose X subject to AX is at most B, the dual then looks like min of the same B, B transpose Y, subject to A transpose Y is equal to C, and Y is non-negative everywhere. Okay. And I did mention in class last time that, okay, yes, like this is the kind of one way, I called it the, type alpha and type beta type ways of writing down the primal. So here I insist that every inequality be a less than or equal to, which is not true there, right? Here I have a bunch of greater than or equal to's. And I also have a bunch of equalities. Now, f is at least 0 is the same thing as minus f is at most 0. So I could turn that into an inequality in that direction. What about equalities? Well, x is equal to y is the same thing as x is at most y, and minus x is at most minus y. So I could turn each equality into 2 inequalities in both directions. Okay, that would fit this format, and then I could just immediately apply kind of this mechanical procedure to form the dual. Okay. I could also go back to how we define the dual in the first place, and show you kind of what other kind of tricks, like little shortcuts that lets you realize how to deal with equalities and how to deal with non-negativity constraints. Just remember where the dual came from. Where did the dual come from? Remember we said we wanted to max sum of CIXI subject to constraints that look like sum of, let's say, A1IXI is at most B1, sum of A2IXI is at most B2, etc. Right? That's exactly that format. And then we said, let's multiply every constraint by some number. So y1 put here times y1, y2 here times y2. And then we added them all up. And when we added them all up, as long as the y's were non-negative, it didn't flip the sign of the inequality. And we got that here. We basically got B transpose Y on the right-hand side. And on the left-hand side, we got that we got x1 times A11 y1 plus A21 y2 plus A31 y3, etc., plus x2 times A12 y1 plus plus A22 y2, etc. Right? So we got something that looked like this. This is where the dual came from. And we said, look, if we can make this equal to C1, and we can make this equal to C2, etc., then this left-hand side is just C transpose X. And what we're saying is C transpose X is at most B transpose Y. So we just proved an upper bound on the value of the primal, on the optimal value of the primal. Right? Namely, B transpose Y. So let's get the best upper bound we can have by minimizing the right-hand side. Let's minimize B transpose Y, subject to the constraint that all these coefficients here have to equal the corresponding coefficients in C. And the y's have to have non-negative entries to make sure we don't flip the signs. We don't flip the signs of the inequalities. Okay? So now let's think about what we have here. Some of our constraints are not inequalities, they're equalities. Right? So for example, one of them actually is an equality. What does that mean for us? It means in particular, it doesn't matter whether y2 is at least 0. Right? We said that all the y's have to be at least 0 because we were worried about flipping the sign of the inequality. Right? But if it's not an equality, if it's an equality already, I mean, not flip the sign, flip the direction. If it's an equality already, there's no direction to flip. So we don't care whether y2 is non-negative. So basically, when you have equalities like that, it means that the corresponding variables in the dual don't have to have the inequality constraint. I mean, they don't have to have the non-negativity constraint. Okay? Another thing, too, is over here, we have this thing where all the variables have to be non-negative, right? This is saying that, f1 is minus f1 is at most 0, minus f2 is at most 0, minus f3 is at most 0, etc. So imagine that we had such things here. We also had that minus x1 is at most 0, minus x2 is at most 0, etc. And we have some dual variables that we're multiplying there. Those are also some more y's. Let me just call these dual variables a different letter. Those are the dual variables that correspond to the non-negativity constraints of x. If we, for example, had some extra constraint here that x has to be at least 0, which is what we have over there, what would that mean over here? So now we have some variables that look like w1 times this is at most 0 times w1, which is just 0. w2 times this is also at most 0, etc. And these would get added in, right? So here we would have minus w1, right? Here we have minus w2, etc. And what I'm saying is that This thing, a1y1 plus a2a11y1 plus a21y2 plus minus w1 has to equal c1. a12y1 plus a22y2 blah, 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 minus w2 has to equal c2. But the only constraint on w is, again, the w's also have to be non-negative. That's the only constraint. And the w's do not appear at all in the objective function. Why not? Because their right-hand sides are 0, right? So, I mean, yes, they sort of do appear, but they appear with a 0 coefficient. So really, I'm trying to minimize b transpose y plus 0 times w1 plus 0 times w2 plus 0 times w3, because the b's here are all zeros. Okay. So good. So I have these. So basically what that means is I have these w's which have to be non-negative. They don't contribute at all to the the objective function, which means that this part here, these variables, it's enough to say that this thing here, without the w1, just has to be at least c1. Right? Because I have this number minus a non-negative number equals c1, which means that this number has to be at least c1, because when I subtract off this non-negative number w1, it's equal to c1. So now let's try to write the dual. So I'm trying to minimize b transpose y. And actually, I don't want to be, so I call these w's. Let me actually just call them z's. It's going to, because I want to use w for something else soon. Okay. So what's the dual? First of all, remember, every constraint in the primal gives a variable in the dual. And similarly, every variable in the primal gives a constraint in the dual. Okay? Because this matrix is A transpose, which means the old number of variables is now the new number of constraints, and the old number of constraints is now the new number of variables. So other than the non-negativity constraints, I really only have two kinds of constraints up there. I have capacity constraints, and I have flow conservation constraints. How many do I have? I have m capacity constraints, and I have n minus 2 flow conservation constraints. Right? I don't have one for S or T. So let me call these the W's, and let me call these the Y's. They're all just variables in the dual. I just want to give them, remember, each constraint gives me a variable in the dual. Since there are two kinds of constraints, it makes sense for me to use two different letters for those two different kinds of variables in the dual. The variables that came from the capacity constraints and the variables that came from the flow conservation constraints. I'm going to call those the Y's and the W's. So we know that the right-hand side in the primal becomes the cost vector in the dual. So that's the 3, the 2. It's basically those capacities. And then, of course, all the other right-hand sides are 0, so they don't matter in the cost function. So I want to minimize 3. Again, so 3 now is the 3 times, that's that 3, times FSA, times YSA, plus one times YAT so basically it's just going to be, for each edge, have the variable for that edge times the capacity. So I said YSA, AT, I also need SB, plus 2 times YSB plus 3 times YBT plus, there's one left, I think, which I'm missing, is AB, 1 times YAB. Okay, so minimize that. And then I also have plus 0, plus 0 times WA plus 0 times WB, right? Because the right-hand sides here are 0 and 0, but they don't matter because 0 is not affecting the cost of the dual. Okay. And then now, how many constraints do I have? Remember, variables in the primal become constraints in the dual, right? So I had m variables in the primal, 1 per edge, which means I have m constraints in the dual. I have 1 constraint per edge. And you can just apply this mechanically, right? There's like a formula for getting the dual. Let me just write out what you would get if you did that. Subject to YSA plus WA is at least 1. YSB plus WB is at least 1. These correspond to the edges leaving S. And then for the edges that don't leave S, they leave things in the middle, you'd get, for example, YAB minus WA plus WB is at least 0. Here I have an et cetera. And here I, for example, have an AB doesn't involve S, right? And I also have the constraint that Y is at least 0. What's going on here? As I said before, normally in the dual you have these equality constraints. But because these constraints are equality instead of inequality, as I said over there, the corresponding dual variables don't have non-negativity constraints. Okay. So for example, that constraint corresponds to WA, and that constraint corresponds to WB. So we don't have the non-negativity constraints on WA and WB. But we do have them on the Ys. Because the Ys came from the capacity constraints, which are inequalities. And similarly, we also have these greater than or equal to's instead of equalities because of the f at least 0 constraint. Since we have the f at least 0 constraint, there are these hidden variables in the dual that don't really matter, so I didn't write them over there, that basically all these z's had to be non-negative, and we're allowed to use them to bring us down to equal c. Which means that this sum here has to be at least c. Okay, so this just looks like some stuff. Now, imagine I knew that all the y's and the w's are all 0, 1 variables. Of course I don't. In fact, the y's and the w's don't even have to be integers. For all I know, maybe YSA is going to be a third. If I knew that, then I could interpret them in the following way. I could say, look, YAB is equal to 1 if AB crosses the cut, and 0 otherwise. And WA is equal to 1 if A is on the S side of the cut. Okay. And then these constraints make sense. It's like I pay the capacity for each, so if y is on 0s and 1s, I pay the capacity, so if it's 0, then it disappears. If it's 1, that means that edge is crossing the cut. Right? So underline, so it crosses some cut. Okay, good. So let's say there's some cut now, ST. This thing is 1 if it crosses the cut. and then I pick up the capacity of that edge, and otherwise I get 0. So this would just be the value of the cut. It'd be the capacity. This whole thing here would be the capacity of that cut. And these constraints are basically forcing me to set the y's and w's that are consistent with the cut. Okay? Or actually, said a different way, I could basically, I'm saying if I knew there were 0, 1 variables, what I could just define is, I could define a cut. I can define a cut S, where S is the set of all A such that WA is 1. And then I claim that the constraints force YE to be 1 if E crosses the cut in the S to T direction. And then I would have actually the value of the cut. So let's look at this. Why does this force me to set to 1 all the y's that cross the cut? Well, let's look at the edges leaving S. Is A, let's say that A is not on the side of the cut. Okay? Sorry, A is not on the S side of the cut. That means WA by definition is 0. But this sum has to be at least 1, which forces me to set YSA to be 1, which forces me to acknowledge that SA is actually crossing the cut. And the same thing down here. Likewise, if WA is 1, meaning that A is on the S side, then this is already making it at least 1. So there's no incentive for me to set YSA to be 1 in optimal solution. Why not? Because if I set YSA to be 1, I pick up a 3 here. All these capacities are non-negative. And I'm trying to minimize my objective, right? I'm trying as much as possible to set all the y's to 0. If I set all the y's to 0, I am very happy because that means my objective value is 0. Okay, so if WA is already 1, I can keep YSA to be 0, and I'm happy because I satisfy the constraint. But if WA is 0, meaning A is on the other side of the cut, I'm forced to set YSA to be 1 to make this constraint satisfied. Now let's look at the constraints that correspond to vertices which are not S, like middle vertices. So I have things like YAB minus WA plus WB is at least 0. Okay. There's one constraint per edge. Now, the interesting case, so there are basically 4 possibilities for WA and WB. They're either both 1, both 0, A is 1 and B is 0, or A is 0 and B is 1. In 3 of these cases, this part alone is already non-negative, right? So for example, if it's 0, 0, or if it's 1, 1, or if it's 0, 1, then this is either 0 or 1, so it's at least 0. So I'm not forced to set this to be 1. The only case where I'm forced to set this to be 1 is when A is 1, and WA is 1, and WB is 0, which means A is on the S side of the cut, and B is on the T side of the cut. Then this would be minus 1, and I am forced to set YAB to be 1 to make this non-negative. Okay. So this captures min cut. Of course, the problem is there's no guarantee, right? There's no guarantee that the optimal solution will set all the W's to be 0 and 1. Maybe it'll set some of the W's to be a third. In principle. Right. So really we know that, really what we just said is that basically min ST cut is represented by what's called an integer linear program. Right? If we had this linear program, but we said, look, you have to set the variables to be integers, then we would actually have min ST cut. Unfortunately, we don't. So this is some kind of fractional version of min ST cut. And what strong duality says is the optimal value for max flow is equal to the optimal value for this fractional version of min ST cut. On the other hand, we do know by the max flow min-cut theorem that actually the optimal value for max flow is equal to the integer version of min-cut. Okay? So we know that max flow equals integer version of min-cut. We also know that max flow equals fractional optimum for min-cut. So since A is equal to B and A is equal to C, that means that B is equal to C. So the max flow min-cut theorem, together with strong duality, imply that the optimal size of the min-cut is equal to the optimal solution to this fractional version of min-cut. In particular, even though in principle we're allowed to set the y's and w's to be fractions, what this is saying is there's always a solution which is optimal, which is integral. It only needs to set the y's and w's to 0 and 1. It doesn't actually need to set them to be fractions. Okay? But that's, of course, not always true. That's a special property of the min-st-cut fractional linear program, the fact that it has an optimal solution which is integral. Okay? So I think that's all that I'll do for today. You'll see an example of max flow applied to a problem later. Professor Chiesa will start lecturing next week after midterm 2, and he'll show you in a future lecture an example of applying max flow to get what's called an optimal bipartite matching, okay? Maximum bipartite matching. I'm not going to talk about that today, but you'll see that later. Okay? So that's all I have for you today, and good luck on the midterm.